Question: can you prove the small limit theorem in the special case where the function f of z, which you integrate, has a single pole at the point where the circle originates? So let's say z equal to a. So pause the video and try to show that this is indeed true. Quick recap about this small limit theorem. So we have a point A here, and then we have a circular segment centered around A, C little r, with radius little r, which will go towards 0. And then we can calculate the limit of r going towards 0 of the integral over c little r. So this is just the circular segment here, does not include these straight segments. The integral of a function f of z dz happens to be j alpha a, with alpha being the angle here, so that's alpha, and with a being the limit of f of z times z minus a. When z approaches a, this limit happens to be a. So if this is the case, then in the limit, this integral reduces to this particular constant here. So how are we going to tackle this? In case you were stuck, small hint, it's a good idea to try and write our function f of z as a Laurent series. Because since we know that our function has a single pole, that obviously means that our Laurent series will have a certain form. So in case this was the missing link when you were trying to solve this exercise, perhaps it's worthwhile to pause the video again and try and solve the exercise now. Okay, so let's write down the Laurent series of our function f of z. Since it's a function that has a single pole at c minus a, we know that we start at a minus 1. This is the lowest order in our Laurent series. And then we have a constant term a0, and then a1, z minus a, and so on and so forth. We also know something else. We know that this particular limit is true. So let's calculate that now. The limit of z going towards a of f of z times z minus a. Well, you can easily verify for yourself that if you take here this expression of f of z and you multiply by z minus a, then we have for the first term just a 1. And then for all of the other higher order terms, they will have a factor z minus a there. So in the limits of z approaching a, all of these other terms will vanish, which will lead us to the conclusion that a minus 1 is actually this constant a which we introduced here. So we know a little bit more. Right. Next step is trying to calculate that integral using parameterization. So if we do that, we know that z can be written as basically a, the center of the circle, plus r, the radius of the circle, exponential j theta, with then theta running from a certain starting value here to another value, which is basically alpha further. So this is the parameterization of r running around on that little circular segment here. At some point, we will also need to calculate dz. That becomes r exponential j theta, another j d theta. Right, so now we have all the ingredients that we need to try and calculate that integral and then perform the limit operation. So let's see what happens. After parameterization, this becomes a real valued integral from a certain angle theta 1 to another angle theta 2, which is just theta 1 plus alpha. And then we have f of z. So for f of z, we can write that this is equal to a1, which is capital A. That's what we calculated upstairs here. And then we divide by z minus a, and in the parameterization formula here, that's handy, that just becomes r exponential j theta. And Then we keep on looking at the other terms. So that's a naught plus a1, also r exponential j theta, and then some more terms. So that's f of z. Finally, we need to include dz, which we have already calculated. So j r exponential j theta d theta. Good. Now we're basically almost there, because what we're interested in is the limit of r going towards 0. And if you work out this product here, let's start with the first term. This denominator here will cancel. So this will become a constant. So we will end up with an integral of theta 1 to theta 1 plus alpha a, and then we have j d theta. So that's the integral related to the first term. Let's have a look at the other terms, the higher order terms. Well, since every time here we get this multiplication that's going on, all of these terms will have a factor a factor r. And then in the limits of r going towards 0, this means that all of these other higher order terms will cancel. So there's nothing more coming here after. So this is basically the end result of our integral, which is a very trivial integral to calculate. This just becomes j a alpha, which is indeed what we needed to show the small limit theorem, here shown in case our function has a pole of order 1.